Hello, everyone. My name's Nicholas Bussberg. I'm an assistant professor of statistics at Elon University, and I'm excited to be sharing with you my ideas for how to incorporate reproducibility concepts into entry-level courses. This is something that I've started thinking about recently, and I think this is really where our field should be moving in the future. So I'm excited to hear your thoughts on what I have to say, and I'm also excited to listen to the other talks during this symposium. So a little bit about me. Of course, I'm an assistant professor at Elon now, and I do research more on the environmental side of statistics. Things like spatial statistics are what I'm currently focused on. But when I was an undergraduate at Indiana University, I studied biology with a minor in chemistry, and then I moved into a master's in environmental science before I finally got my PhD at IU in statistics. And I want to use some of this background to help frame my talk today. And so particularly in all of the lab sciences like chemistry and biology, I believe they already have a curricular model that we could use for reproducibility. And that model has to do with lab notebooks during lab sessions. And so I pulled some of this information from an MIT page on kind of teaching students about why they should be keeping their laboratory notebooks and what some of the rules are. And I thought this quote was interesting. So they said, could someone else using your notebook to repeat your work and obtain the same results? And in my mind, that's exactly the same goals as reproducibility. We want somebody else to use in our case, our data, our files, to repeat our work and obtain the exact same results. And so the basic goal is the same. And to give you an idea, if you've never had a lab course before, there's a lot of rules that go into this. Some of these, might seem, pretty standard. And of course, some of these we're going to relate today to how we could do reproducibility. But for example, writing legibly, so somebody has to be able to understand what you're writing. Things like dating and numbering every page or every other page. There's rules that's going to depend on your exact discipline and kind of what area, what you need to do. And then the one thing that always stuck to me when I was taking lab courses was putting a single line through mistakes. So you don't obliterate your mistakes, you don't scribble it out, you just put a single line, and you usually have to do something like put your initials next to it and an explanation why you're changing that, why you made the mistake. And then kind of the basics are you're documenting what you're doing and why. And I think we can learn a lot from how disciplines like chemistry teach and incorporate lab notebooks, and we can use that to help us understand something about reproducibility. And so there's a few ideas to hopefully help frame my talk. So the first one is these lab notebook requirements. They start right away. So the very first course you take in chemistry, if it has a lab component with it, is going to have a lab notebook requirement. And they're going to start grading it immediately. In my experience, tends to be pretty strictly as well. So these start right away. I do want to take a moment, when I'm saying entry-level courses, I'm not necessarily saying, for our purposes, like Statistics 101 or something like that, like a statistical literacy course. I'm referring to the kind of the gateway course for your major, the course where you're going to teach some kind of software with it. You're going to do some more standard techniques, some more quantitative analysis. Not that you shouldn't, not that we can't teach and shouldn't teach reproducibility in those early courses, but I'm thinking about this more from when you're introducing computing. And so lab sciences tend to do this very early on. They start teaching this and grading this. And the second one is, since they're starting this early on, these same requirements get reinforced throughout the rest of the curriculum. This isn't just the first course they teach, in this case, lab notebooks, and then they're done. They keep doing this throughout, and it's expected that by the time you get to advanced courses, you have a basic idea on how to keep a lab notebook. You don't need to be taught the general rules. It might vary a little bit. There might be some more advanced things or some nuances with new machines or techniques you're using, but the basic foundations are going to be the same. And what that means is that the department has to agree on what those rules are, of what are we going to enforce. And really, in places like chemistry, biology, physics, geology, they have pretty broad standards in the field of what they want from a lab notebook. And even across disciplines, they have that. And this is something that I think we should start implementing when we're talking about quantitative analysis of what are those basic rules that we agree on, and what do we want students to learn by the time they graduate. And I know that right now, changing the field or getting broad agreement with the field is a little bit much, but if we could start with our own departments, get some rules for reproducibility, that would be a good place to start. And then the third idea that we can take from this is that students, the goal is for students to start building the habit of taking notes. So the reason why this starts getting implemented throughout the rest of the curriculum, why these lab notebook requirements are expected, is because they have to do this moving forward. Students need to be in the habit of taking these notes. After they graduate, if they get jobs working in a lab somewhere, they have to take notes in a lab notebook, and most of the rules are pretty commonplace. I worked in graduate school. I got a job working in an analytical geochemistry lab, and on the first day when we started learning, the particular machines or what I would be doing, there was a lab notebook there, and the faculty who was running the lab said, well, you remember learning about those lab notebook requirements in chemistry. Here's how I would like this to be done. It wasn't, let me teach you about how to do a lab notebook. It was, I'm assuming since you've had chemistry before, since you've taken some of these lab courses, that you already know the basics, the foundations. All I needed to do is teach you the particular nuances to how I want to keep the lab notebook. And I think this is the same with reproducibility. I think we could build a framework that students could use, and then when they go get a job, the job teaches them the specifics on what tools, what methods, what policies they need to follow, so that way they can just easily adapt their workflow to match whatever their new work requirements are. And that's whether they're going into academia or grad school or research or working in industry. There should be this expectation that you're going to do reproducible work. And then the fourth idea, I do want to say this metaphor is in many ways too simplistic for what we need with reproducibility. So for example, in labs, students already know how to write. Chemistry classes aren't teaching students how to say, write the words. They're just teaching them how to format them and what policies they need to do. The problem is in our quantitative courses, particularly in entry courses, we're probably teaching them how to write through learning software. Most students don't come into our entry-level courses knowing the software, knowing how to code if we're doing something that has code. So we have to not only teach them the rules of, say, reproducibility, of how to do this effectively, we're also teaching them the basics of how to write. And so that's going to complicate things. And this is why I'm going to advocate, and you'll see this throughout my talk, that we start slowly, that we build foundations, and then over time we can work in the more complex reproducibility tools and workflows. The other issue that lab sciences benefit from is they usually have a dedicated, at least a lab component that goes along with the class, if not an entirely separate lab class. We generally don't have that in our quantitative analysis classes, whether you're in statistics like me, or you're teaching economics or psychology. Usually all of that's built into your standard 3 or 4 credit hour class. You usually don't have an extra 2 credit hours where you're solely dedicated to doing computing. And so that puts us immediately at a little bit of a disadvantage on, we're already crunched for time. Now we have to add in how to teach code, how to teach the software, and we're trying to advocate, in this talk at least, to teaching reproducibility. So we don't have that dedicated component to our courses where we could put that in. And so, as I tell from my talk, and as I've already mentioned, what I'm going to talk about is mainly on this first idea of why we should be starting reproducibility early. And so to provide some motivation for this, I think, and I think I'm preaching to the choir here, there's broad agreement that across disciplines that reproducibility is important for students to learn, that when they graduate, they should be able to compute in a way that is reproducible. Their analyses should be able to be replicated, that these are important concepts, not just for students to know, but also for them to be able to practice. And so then the questions really become, when do we introduce this reproducibility to our students, and how do we teach reproducibility to them? Or another way of phrasing that would just be, what techniques do they need to learn? And I do, of course, recognize that these two questions are very much related. If we're advocating, and of course in this talk, I'm advocating that we teach reproducibility to students very early on, well, then the techniques are going to have to be scaled back a little bit. And I'll be talking a little bit about that throughout, about how we can scale back advanced tools and methods. I do want to take the moment before I get into addressing these questions to mention that I am coming at this from teaching at kind of the college level, at the undergraduate level currently. Although I think these ideas could easily be applied and probably should be applied in the K-12 system. Right now, I'm going to focus more on kind of college level courses, particularly undergraduate. And then I'm also coming at this from a statistics perspective, but I do think all of these could be applied and should be applied in every quantitative discipline. Again, if you're in economics, you know, your kind of your gateway economics course where you are teaching some computing with it, I think reproducibility should be a part of that. So I do apologize if I drift into talking about, say, intro stats courses, but I do mean that to say any kind of intro quantitative computing type course. Okay, so we'll start with kind of the first goal. And it's not just that I'm going to be advocating for entry-level courses to start reproducibility, it's that reproducibility should really be in all courses. And so, you know, kind of a bait and switch there, I guess, of it's not just entry-level, it is all courses that I'm going to advocate for. And so again, if we're in such broad agreement that reproducibility is important for students, that it is a vital component of how we do quantitative analysis, then it should make sense that we integrate this into all of our courses. It should just be the way you do computing, the way you do your quantitative analysis, the way you work should be in a reproducible way. That should be the standard. And of course, I'm advocating that that should be in entry-level courses. And I think one of the benefits to this is if we include this, if we start the foundation in entry-level courses, and we continue it through advanced courses, we're still going to have enough time to be able to teach other content, the other content that we are required to teach. And this is particularly important in early courses where there's an entire field, in my case, of statistics that we want to teach. And so there's tons of content that goes into those entry-level courses. And we don't have time to take a huge section of the class or the entire class to talk about reproducibility. So we have to be able to weave it in there. But if we kind of start scaffolding this throughout our curriculum, we can start more simply and start with the basics. And then we can layer on more specific tools for our majors in the advanced courses. We can teach them whatever they might need in reproducibility to be able to succeed in their careers, whether that's grad school or whether that's going on and taking a job right away. And I also think that if it's so vital to our fields that, again, that we have reproducible results, then I would think that if another student, in my case, not a statistics student, was to take a statistics class, they should learn something about reproducibility. If that is so important to our field, that the way you do statistics should be reproducible, then one of the takeaways from our course is that, you know, statistics should be reproducible, and they should learn something about that at a minimum of just understanding the concept, and that this should be the standard. But ideally, if they're going to take one of our courses with computing, they learn some techniques on how to do that. And I think it will help them in their own major not just in their statistics course, but I think will help them later on. Okay. The second reason has to do with start developing good habits. So what I found when I taught the graduate course on reproducibility is I'm teaching graduate students, and a lot of them have really bad habits because they've never learned reproducibility before. This is the first class, the first time that they've really thought about how do I do reproducible analysis. And so if we're starting students out with bad habits, it's going to be harder to break later on. So if we just start students right away, once you start learning computing, this is just the way, the expectation of how you do analysis. And then they're going to start expecting this later on in courses. Students are going to start just doing this because this is the way you do it. You know, you look at, say, chemistry, I didn't move into my job working for the geology faculty thinking that I wouldn't have to do a lab notebook. I knew I'm going to be working in a lab. Of course, I'm going to have to be documenting my work. Of course, that's going to have to be in a lab notebook. Now, it was a little different than what I had experienced before, but the basics were still there. I had that expectation that I was going to have to use this if I was ever going to get a job and keep a job in that area. And I think the same thing should apply to reproducibility. If our students are starting out with bad habits, it's going to be really hard for them to move on from that later on. So we want them to start developing that as soon as they can. And we also don't want the mentality for reproducibility that it's only important in this particular setting. And, you know, for example, if we have a standalone reproducibility course or just a reproducibility lecture, and that's the only time they experience reproducibility, it seems more like a side topic there. It seems more like just this additional tool to put in your toolbox. Sometimes you'll need it and sometimes you won't, but that's not really true. Reproducibility should be integrated throughout the way we do quantitative research. And so it should be to some level in all of our classes. And this is, again, this is not to suggest I'm not suggesting that we get rid of standalone reproducibility courses or lectures. I think they're really vital. I'm developing one myself. I just think that the reproducibility concept should be introduced and enforced in all of the other classes. And then maybe these standalone courses could serve more as teaching more advanced techniques specific to that field. And so that's more of the idea here. And then kind of the third reason why I think that reproducibility should be in all of our courses and entry-level courses is I think this is really crucial for all students. And I think that's one of the big focuses, or one of the main points rather, for this symposium, is that this is important even just beyond reproducibility itself. It's just important to have these techniques. And even though that's not the point of this talk to kind of delve into why students may benefit from reproducibility, even if they're not in our discipline, this is still something to consider. And in particular, as teaching statistics, we often have lots of students who aren't our majors that take our courses. So maybe they're just getting a minor in statistics, or maybe they're just taking 1 or 2 courses. But again, if they're going to learn statistics, they should learn the way we do statistics properly, and that should include reproducibility. But also these students likely, if they're not, in my case, a statistician, they're not going to go on to do that, then they're probably not going to use the advanced tools that are more specific to our discipline. So in my case, that might be something like Github or R Markdown. And so is it really appropriate to be teaching those tools in entry-level courses? And I'm going to talk about that later on in this presentation, and some ideas on how we could scale that back. And so the idea should be that for teaching reproducibility in these entry-level courses, it should be accessible to people not in our discipline, to our outside students, outside majors, and this should be flexible enough to incorporate into any course or discipline. All right, and so I do want to take just a couple moments to talk about the issue with entry-level courses, because it's not just as easy as just teach reproducibility and it's fine. There's a lot of challenges when it comes to these entry-level courses. And so I pulled some of this from the American Statistical Association. They have a listserv on statistics and data science education. And somebody posed the question of how do people teach intro stats in four-year institutions? And this is by no means a random sample, but I just wanted to compile some of these results to give an idea of what we're dealing with, of when we have to incorporate reproducibility into this. So there's a few departments and institutions that have a computing lab, either built within their course or an extra one, but there's many that do not have a lab. In my case, this semester and this year, I might be in a lab classroom, although I wasn't last semester, but I am this semester, but there really isn't a dedicated lab component. It's not like on Tuesday nights we go to do computing lab. That's just something that has to get integrated through the rest of the course. From software, it's really anything that you have available. So there's people that are using, say, StatCrunch, which is built into, say, MyStatLab. There's some programs that are using Excel. R is very common. Of course, SAS, Stata, pretty much every software you can imagine is probably being taught. And so whatever reproducibility that we're trying to incorporate has to match some of these different programs or be able to be integrated with it. In statistics in particular, we have faculty who aren't in the statistics department who teach our entry-level statistics courses. So we have faculty that aren't statisticians, have different levels of experiences with stats. They come from different disciplines and backgrounds. Even within the people who are statisticians, there's different backgrounds and comfort level with different topics, including reproducibility. And then you can imagine if that's faculty, the students are all over the place on their backgrounds, particularly when it comes to statistics, and most of them have never even heard of reproducibility. And then, as is with all entry-level courses, as I mentioned, there's so much content to cover. Again, you have an entire field in front of you. So common things in my courses are things like t-tests, ANOVA, regression, chi-squared. But in your courses, you might be teaching something more specific to your discipline. But you have to cover this core content, and you have to get through it because it's expected that if they go on to take other courses, they're going to need to be able to use those. And then the last thing is the class size is going to range from small classes where you might be able to get to know students more quickly to really large classes. And so whatever we're doing, we have to be able to adapt it in all of these courses. And so we need something that's simple enough that it could be implemented in those. And what I'm going to suggest in this talk is that we should focus on core reproducibility principles. And so what I mean by that is, let's think about, what do you need to have reproducibility? If we're going to boil it down, I mean, there's a lot of things we'd like to have, but if we boil it down, we need to have the data. You need to have the data set that you used to get the results. Ideally, we'd have reproducible script files, but of course, I mentioned things like Excel in the previous page. You don't have script files really, especially when you're teaching it in entry-level courses. And so, you at least need to have the Excel file and some really detailed documentation of how you got those results. But even if you did have script files, you should still have at least some explanation or documentation on how to use the files or on which order to run them. So this is kind of at the core of what I believe is needed for reproducibility. And so I'm going to frame this as kind of two key principles then. And the first one that I'm going to talk about is reproducible, robust, and legible code. And I will discuss, if you're using some software like Excel where you don't really have this code, of some ways you could still introduce reproducibility and have that there. I do acknowledge that that's just kind of a state of where programs are. Whether or not you like Excel, I personally use Excel, but I don't really think it's a statistical software, and it's incredibly difficult to be reproducible. But I acknowledge that there's a lot of businesses that are using it. A lot of students are going to go to work for somebody who's going to require them to use Excel. And so there is some value in teaching students how to deal with that situation. And so that's the first principle. The second one is what I'm going to call the posting principle, and I get this from Scott Long at Indiana University. And I'll introduce that later and talk about that, but I'm going to start with reproducible, robust, and legible code. And so define these terms. So reproducible is just that your program should generate the identical results. So if you rerun your program, you should get exactly the same results that you got the first time. Most of us are probably aware of that definition. What I mean by robust is that your program should be able to run on another computer, not just on your system, but if I run it on a different computer, I shouldn't have to modify it to be able to get it to run. And so the primary catch with this is usually you can't hard code your working directory within your script files. So using things like relative pathing is important. And the second thing with robust, which is maybe we have 1A, 1B, like 1A is the program should be able to run without modification, and the 1B is files really shouldn't be fragile in the sense that they're dependent on having data stored in the software's memory. So things like data sets and variables, if you're counting on that already be in there, well, in the previous file that you ran, you can just save that file and then load that directly. That creates a more robust structure. But also things like random number generators are important. And things like setting the seed for those random number generators. So you're not just relying on when you ran it, but actually telling the system. And that seems basic to us, but students aren't aware a lot of this. And these are both good examples of students building bad habits. If we taught students, we never even introduced hard coding working directories in kind of the first place, and we taught them to set that outside of the script files, and you set it relative to where you're working, and then you use relative pathing after it, that's just going to be the way students work after that. They're not going to learn bad habits or Google something and then develop bad habits. They're just going to use the rules and the policies we set forward. Same thing with not depending on system settings and using things like setting the seed for random number generators. The last thing is legible. You'll notice this was one of the rules that we had for chemistry notebooks. And so our program should be understandable, just like lab notebooks should be readable to somebody else, and somebody else should be able to read it and use it. Same thing with our code. It should be understandable and readable to somebody else. And I like to tell students that includes the future you of when you come back to this, you want to be able to understand what you did. And there's lots of things that go into this, but of course, using comments is one of them, but also using templates or just teaching students standard practices. So things like maybe indentation is important, or particular notation or features about the particular software, like line wrapping and making sure you have easily understandable variable and data set names. These are all kind of important things that help make your code more legible. And I actually find that these three ideas are relatively easy to implement with some careful planning into entry-level courses. And so, for example, this semester, when I was teaching SAS for my entry-level statistics course, I had a student during class ask me about spaces after the equal sign in one of the options, and just asked if, I said I had a space there, what happens if you don't have a space? And so it's just a good practice, with the class, I deleted the space and reran it. And of course, in SAS, nothing changes because SAS doesn't really care about that white space. And so it's just a good setting to be able to introduce to the students of like, SAS doesn't care, but what I use these spaces for is to make the code easier to read for me and for somebody else. Just because you can do something doesn't necessarily mean you should. Sometimes spaces help things, sometimes they don't. But those are the decisions, and making it easier to read is a really important part of doing code. And so there are some ways of kind of integrating this into coursework. And I'm going to start out with some ideas I have on kind of no stakes or lower stakes assignments of how to integrate this. And of course, you could start with, doing a lecture on reproducibility and the rules and the importance of this. You could do things like have a handout for rules of computing. And again, that might seem odd, but chemistry does that. The link I had before was from MIT for lab notebooks. That was what they did. They had rules. This is what has to be done when you go into the lab. And so students could just have kind of this handout on this is how you compute. This is what you have to do when you approach doing analysis. And yes, it might take some time to get used to it, to develop the habit, but you should start practicing it right away. And something I realized this semester, and I'm kicking myself for not thinking about it earlier, and particularly last semester too, but this semester, but a student emailed me essentially saying that she had some issues with her code and she didn't know what was wrong, but she also didn't know how to ask me questions. So she just wanted to meet with me after class or during office hours. And I realized I could be taking that opportunity to be teaching students how to ask questions about their code. And so, for example, what I told my classes the next day is it's really helpful if they copy their code or they screenshot it. And the reason it's helpful is so that I can reproduce their errors. And I use the term reproduce so that way they start thinking about this of what I'm going to do is I'm going to take your code, I'm going to run it. I want to see your error. I want to get the results that you got, and then I can troubleshoot it and help you identify it. So even when they're doing things like thinking about how to ask about code, they're developing this habit of copying their code because that's what it's important. What's important is not necessarily the error message or the result. It's the code that you use to get there. And then I'm going to try to reproduce that to be able to diagnose it. And so I think moving forward, I'm going to be integrating this into the syllabus or when I introduce the software to tell students how they can be asking questions about this. And I've also done things like creating templates for students. So I have templates for SAS and I tell students, please use this, please just copy this because this is the structure, this is how it works. And it also provides a nice way to talk about comments because my templates have comments in them and to tell students how they can update this. You could also have students create their own templates. You could do things like peer review where you have students run each other's code to make sure it runs. You could have students paste their code into assignments. That's something I'm trying to do more where anytime they do anything in SAS, they need to copy that into the homework. And they're going to get points for doing that, for just that simple thing of pasting their code. And I tell them this is essentially like showing your work. This is like, writing out the formula. This helps me give you partial credit. And of course, that's the grade component students care about. But more importantly, it helps me understand how you got there. And I can identify ways of maybe doing this more efficiently in the future. And then there are some higher stakes assignments. So you could start grading students on a lot of this. And I did this when I was teaching the graduate course on reproducibility. I had them create their own templates. Those templates had to run, maybe just do a simple regression, but they had to create their own templates that had to work. And I graded them on, kind of how well they did there. And then I also graded them on whether or not the code ran. And if it didn't run, particularly for graduate students, you got a 0. It's, particularly in a class on reproducibility, when that is the goal, your code better run because that's the main point of the class. Now in entry-level courses, you might relax some of that. It might not be an automatic 0, but it's the same thing of your code needs to run. It's really important that if you say these are the results you got, then you should be able to do it again. And so there could be some grade component there where the code needs to run and generate the same results. And if you have time in an entry-level course, I know I don't really have time to do a full reproducibility or replication assignment, but you might, depending on what you're doing. This is a good, a good assignment to give students kind of the idea of how hard it is sometimes to reproduce or replicate results. And so this is, I think there's some other talks during the symposium that are going to give some examples, and there's good ideas on Projecteer's website, and you can find them elsewhere too. But these are great assignments. Unfortunately, in entry-level courses, you start running into how much time do you have to dedicate to strictly reproducibility, and this might be a little bit too much depending on how much content you have to teach. Okay, so if you aren't using script-based software, so what I've said before is mainly for programs maybe like SAS or Stata or R, where you do have some code that you could copy. But if you're using something like Excel or even SPSS, even though SPSS has the syntax files, a lot of time it's just taught more as like a point and click. So you could still do some of this thing and still talk about the importance of reproducibility, of course, and kind of having this robust legible code. So kind of starting, you could just have the same discussions or lectures or handouts, and you could even talk about the benefits of using script-based software later on. Of course, you're not using it in this course for you know, you could give your reason of why you're using, say, Excel, but eventually maybe they might be exposed to script-based software, and you could talk about the benefits of doing that. You could still have students, instead of pasting their code, they wouldn't have that necessarily for something like Excel, but they would have that, they would be able to upload their Excel files. Instead of code, they could be writing more detailed documentation, more things like README files that explain what they did and why. And they could do practice exercises. And so I got from a coworker, it's called the peanut butter and jelly replication activity, where you essentially divide students into groups and you have them write a recipe for how to make a peanut butter and jelly sandwich. And then you take those, you know, they write it on a piece of paper, you give the paper to another group, and then those groups try to really be detailed and dig holes in it. So like when you say put the two halves of the bread together with the peanut butter and jelly, does the peanut butter and jelly go on the inside of the sandwich or on the outside? And so you can really just start playing around with that of how detailed you have to be to really reproduce the results of getting a peanut butter and jelly sandwich. That there's a lot of tacit knowledge there that we assume, and if you were really taking it literally, you might not create a peanut butter and jelly sandwich, or at least what we normally think of it. And so I want to switch now to talking about talking about the posting principle, but I want to provide a little bit of motivation before I do it. So when I discuss reproducibility, particularly with statisticians, I normally hear two tools mentioned. The first is Git or GitHub, and the second is R Markdown. And I do have a couple issues with these tools in entry-level courses. Now, of course, I support these tools in more advanced coursework, and I think it's important particularly for statisticians to at least be aware of them. But in entry-level courses, there's a couple of issues. The first one is using these tools does not guarantee reproducibility. You still have to teach other things. And they're difficult, or there's at least a relatively steep learning curve to use them. And we're already teaching them how to code in the first place. Teaching them something else on top of that is going to start getting too much for an intro course. And then in entry-level courses, they're not all our students. And so many students may not have any need to even be aware that these tools exist. And so we need to think about our student base and why they're using it. So I'm going to talk about GitHub and kind of a solution to some of that in GitHub. And so in case you haven't seen GitHub before, the few benefits of it, it's cloud storage. There's built-in version control with your files. There's this system with kind of the terms commit, fork, and merge, where essentially you're ensuring that files aren't overwritten. You can actually compare two versions of a file and decide which pieces you want to merge together if there's any conflict between them, which really makes it really great for collaborative work. The issue is, like learning those terms is one of them, kind of this steep learning curve, but it also requires a lot of other knowledge to be able to run properly. So One of the things with Git is usually you're using like the Unix shell, the command line on your computer to be able to run and push these files up to the server. And so we want to be able to have an alternative to this. So this is kind of the complex tool that's normally suggested. And the alternative is what Scott Long calls the posting principle. And it's really defined by two rules. The first one is the share rule, where you can only share results after files are posted. And the second one is the no change rule, where once a file is posted, you can't change it. And I'll define this in a second. I know posting still doesn't really make sense. But the first reproducibility principle, the robust and legible code, that's more about generating identical results, assuming you have the code and the data. The second principle, this posting principle, is more about the ability, you need to be able to find that data and not overwrite the same data set. And so we need some way of dealing with that. And so what this posting principle is, or how you design this. So say I have a folder for a particular project. I have two directories in there. I have one called work and one called posted. I have them represented here in folders. And work is, as you can imagine, this is where I'm doing my analysis. I'm cleaning my data, I'm running regression, I'm doing whatever I'm doing. And then let's say I'm ready to share this with somebody. And remember, the first rule is the share rule. So anytime you share it, it has to be posted. So I'm either ready to share it with my collaborators, I'm ready to publish it, I'm ready, maybe I'm just at a stopping point. And so what I do is I move that file from work, I move it into my posted folder. And so now that it's in posted, now I can share it. But let's say I need to modify that file. So I get comments back from my collaborators and they want me to adjust the analysis. Well, I copy that. So I'm not moving it from posted, but I'm copying it from posted. And I'm copying that into work, and then I'm renaming it. Because remember, once a file is posted, I can't change it. So that original file is going to stay in posted. But I also can't have two files with the same name. So I need to rename that to something else. And you can kind of do this with things, like versions, numbers, or dates. And so the nice thing with this posting rule, assuming you follow this procedure, is this essentially serves a lot of the same purposes as GitHub does. Posting, this concept of posting files, of moving it from work into posted, is essentially the commit system in GitHub. And then if you have thoughtful naming, like I was mentioning with version number or dates, you also get this version control. So you don't have two or more files with the same name. And I hope you can see the benefits are anybody can do this. You just have to create these directories on your own computer. And it could be on your computer, it could be on a cloud service. You can do this and adapt this for collaborations and have shared folders. It's of course scalable from, say, small homework assignments to larger projects. And so anybody can implement this principle. The key is here you have to stay disciplined. But this is just following the rules. So this posting principle, unlike GitHub, where a lot of it's automated, you have to follow these rules. Whatever rules you're going to create, you have to follow them. And so you also need, since you might be storing these files on your own computer, you also need a backup plan. And if you're doing collaborations, this requires a little bit more planning. And so you have that trade-off with GitHub, where GitHub has a lot of these features built in. And now you have to design them from scratch and really follow your own rules. But the benefit, kind of that trade-off, is anybody can do this. There's almost no learning curve other than sticking with this particular rule. And that's really no different than kind of the lab notebooks. There's rules you have to follow. There's nothing to prevent students from not following the rules, but it is kind of that expectation. If you don't follow the rules, you'll maybe fail or not graduate with a chemistry degree, not be accepted into grad school and not be able to publish, might not get tenure, that kind of thing. That's already built into the system to help enforce those rules, to enforce that you follow them. And now, of course, like implementing this into entry-level courses is a little tricky because this is more dependent on students just following the structure. And so you could have, of course, put this into kind of a short lecture or a classroom discussion or a handout. But what I've done before is you could create a cloud directory where students have to have their own personal working folder and use this posting system. I mean, they can bypass that too, but I like to encourage them to at least try it out for a semester and see what you think, get a feel for this, and really think about why this is important. But I also find this discussion pairs nicely and is reinforced talking about things like file naming. If I don't want these really annoying file names like my final version 5 underscore final underscore edit underscore done version 2, I want this to be concise. You should be thinking through what your files are named. It also pairs nicely with things like run order naming and version control and backing up your files, all of which could easily be integrated into an entry-level coursework, even if it's just a handout or kind of a side lecture that they're learning about some good ways of backing up their files. It kind of helps reinforce this idea that you need to have your files. If you don't have your files, you can't have reproducible results. And that also includes overwriting your files. So whether you delete the data, you can't find the data, or you overwrite the data, it's all the same result. It's not reproducible because you don't have that original file. And so there are some other ideas. Those are kind of the main two that I wanted to talk about. And I am starting to get low on time. But there's other things you could talk about, like keeping proper documentation, how to work effectively in collaborations, and the importance of transparent code and data, kind of the ethical implications. All of this could be appropriate in different contexts for entry-level courses. And so kind of the main points from this talk are, I think the earlier we start doing this, the faster the students are going to start building these habits. The easier it's going to be to layer on advanced tools that they might need for their majors. And we don't want to have to break bad habits. That's going to take longer to do than if they just assume that when I do statistics, and so in my case, teach statistics, when you do statistics, then you just have to do have reproducible analysis. That's just part of what it is. And I think one of the other points is relying on just a reproducibility course or a lecture instead of integrating this. I think it sends the wrong message. I think we should be tying this throughout the curriculum because this is a vital part of our fields, and this is the way we should be doing analysis. And so to kind of sideline it to just a single course or a lecture kind of sends the wrong message. And of course, that might be where you have to start in your department. I understand that there's more there than you don't have full control over what's going on in your department. But we could start with a reproducibility course with the goal to try to integrate this throughout. And the main point from this talk is I hope you realize there's accessible alternatives to reproducibility tools like Github and our Markdown that you can integrate into entry-level courses. It might require some careful thought and planning, but we can do this. And the goal is we don't have to do all of this all in the first course. We can layer this on throughout other courses as long as we start building those foundations earlier. And so before I close, I do want to thank Projecteer, Sheffield Methods Institute, and the UK Reproducibility Network for sponsoring this symposium. Again, I'm really looking forward to listening to everybody else's talks. I want to thank Scott Long. He mentored me in reproducibility and taught it to me. Many of the ideas through this talk are based on things that he taught me. And then I also want to give a shout out to Ryan Van Krevlin, a coworker at Elon. He gave me the peanut butter and jelly activity, which has been successful in several of the courses I've taught. And so I do recommend that. So I thank you for listening to this. And I look forward to discussing this with you during the live discussion and hearing the rest of the talks for the symposium. So thank you.